Okay, so in conjunction with the previous video where we took a look at kinematics, this is the graphing of kinematics. So this is a baby spoon-fed introduction into what exactly we're looking for. If you pay very close attention to this, you'll be very much prepared for the quizzes and tests that involve these type of graphs from this point on. The first thing that we always got to do is think about rise over run. Yes, this is a very early in your mathematical cycles and of academia, or your other math classes. That's just a way that I say it whenever I stutter. So sorry. So what you've done is understood that the rise over run rule is whenever your slope of a line has a division behind it. But all lines have a division behind it. So we're looking at our rise, which is our y-axis, and our run, which is our x-axis. Here we're looking at something that describes time, and here we're looking at something that describes distance. Distance over time, as mentioned in the earlier video, in an earlier lecture, is speed, or also, if you can also check out your velocity, depending on your displacement. You can look at the change of positions as something is moving. We can also calculate our displacement. So what kind of graph are we looking at if it's distance versus time or distance over time? We, of course, are looking at our velocity graph, its position over time. Now, earlier when some of you were setting up your little SOHCAHTOA problems and you were like, sine inverse cosine O over, or x over 7.3, whatever your hypotenuse was. I always kind of strayed you away and pushed you away from using x as your variables. Because here in algebra, you can always solve for x very easily by making whatever variable you're looking for x. That was a good practice, and that introduced the concept of looking for a variable or solving for a variable during your early stages of your mathematical development. But here, we have an x. And this is an indication that we are dealing with the x-axis, the x plane. If I am walking from east to west or side to side, I am walking on my x plane. So my change of x is my change of position on the x plane, or the x coordinate. If I were to jump upward, which I'm not going to do because I don't want to display my miraculous athletic ability, that would be my y-axis if I were to jump and try to touch the ceiling and then dunk on somebody. But you know, like I said, I'm not going to do that. But this is the x-axis that we're talking about. It's something moving from side to side, or like east and west. So we're talking about the x coordinate plane, my change of position there. So from this point on, when I say change of x, I am talking about my change of position on the x coordinate. Please do not, I promise you, don't do this to where if you're looking for a time, like if there's a problem that's asking for time, that you make x, change of x, or you're trying to look for x, or you make any variable x. In this class in particular, you will get confused. And so I think it's just good practice for you to solve accordingly for whatever letter it is. We use a lowercase t for time, lowercase x for, change of position on that plane. Okay. So, what is the position of the motorcycle? Oh, there you go. I'm giving you a hint of what's going to be on the quiz. After 4 seconds. So, it's not exactly going to be this problem, but it'll be very similar to that. I simply look at my plane right here. There we go. At 4 seconds on my x-axis. Then, bam, I look where it is in conjunction with my y-axis, and I know that it's 30 meters. That is my position of my motorcycle here at 4 seconds. Let's take another question here. What is my velocity from 4 seconds, which is right here, to 1 second, or between 1 and 4 seconds? So I'm going to look over here at 4, and I'm going to look at 1, and it's just everything in between here. Just everything here is what I'm focusing on when it comes to figuring out what my velocity is. I want to find out that specific increment of time. The way we do this is by looking at our change of position in x divided by our change of position in time. And the way we figure out that is we take our final minus our initial. Our final time in the problem says 4. So we put 4 as the first thing that we're going to subtract something from. our initial time that it's asking for is 1. So we take 1 and subtract it there. We subtract 1 from 4 and we get 3 for our change of time. I hope you can keep up with this. If you're not keeping up by now, please rewind just that small increment in that part right there and you'll be fine. Here we have 30 for our final product or our final position, and our initial position at 1 second is 10. So we're going to do 30 minus 10, that gives us 20, divide by 3, and our change of v, or our velocity, is 6.67 meters per second. Once again, our meters are at top because this is what we're measuring here in our distance part, and second is what we're measuring here in our time part. So please, please, please know that. Okay, what are we looking at here? We are looking at a speed versus time graph. And what is speed divided by time? That is an acceleration graph. So yes, this one gets the A for acceleration graph. Please make note that this is what I'm really stressing to you, is that you need to know the difference between the two and how they look and how they communicate with one another. But this is an acceleration graph. What do you notice about the slope of the plane? Of the slope of the line? The slope of this line is negative, and therefore the speed is negative, meaning that the speed is not accelerating. It's not constant acceleration. It's deceleration. Deceleration. So whenever you see a negative slope on a speed and time graph, you're looking at deceleration. What about this one? We have a distance. And the distance, let's just mark it off right here and say that this is 5. We're like 1, 2, 3, 4 over there. Okay, that's really terrible handwriting, which I will fix very shortly. Sorry. Okay, there we go. So we have 5, like, let's say my displacement is at 5. Like, in my classes, I use the example of the grocery store. Like, I'm always at Walmart, and I'm always, you know, friendly to my neighbors who love to finesse as they shop and, you know, get 76 items in the express lane. And I have to sit here and wait while I'm just trying to buy a bottle of water in my grocery cart. Why? I have 3 kids, so that's why I have the cart for just 1 bottle. I know those questions are coming. And I'm just sitting here with the grocery cart. And I'm in the position, so if I moved 5 meters, like, okay, I moved all the way to the end of the line, and then after a while, I just have to sit here and wait. Time is going by, okay? Time is going by, but I'm still in the same position of 5. This is known as zero velocity, that there is no movement whatsoever. I am not changing position at all. So in the previous test, you were tested on this. Most of you got it right. But this is how we graph that. So this isn't just telling me I went 5 meters north, 5 meters east, 5 meters south, 5 meters west, and my displacement is 0. But this is just me sitting still. This is what it's graphing, me sitting still, while I wait for my lovely neighbors of life to finish their purchases, and me waiting and learning patience wonderfully in this cool thing called life. All right, so next, what are we looking at here? It's speed versus time, so it is acceleration. We have a giant A for that. This is an acceleration because we have speed versus time. But it's very different. I'm still moving in a certain area. I'm still moving in a certain direction simply because my speed, let's say my speed here is at 35 miles an hour and it's just constantly there. Here in Siena Plantation, that is the speed limit of the street for the most part. It goes to 35, then 45, then back to 35, just like a little tease. You want to speed a little bit? Okay, nope, back. And that's how I felt when I first started driving here, but that's cool. For the most part, I have to be in the constant speed of 35, and I'm right here at 35, and I'm just there at 35. But I'm still moving, so I'm still changing position. So acceleration is still a vector because I'm still changing position as this, even though the speed is what? Changing, 0 or constant? Constant. This is a constant speed. So when you see a flat line on an acceleration chart, we have constant speed. If you have flat line on a velocity chart, you have zero velocity. You have stillness. Last chart that we see here, and I apologize for that little melon looking thing, that's cool, is distance over time. So immediately we know that we're dealing with what type of chart? That's right, a velocity chart. This is a velocity chart because we have distance and we have time right here. So distance over time, and we see that I'm constantly moving. So this is like, you know, you've been waiting in traffic for a while and finally you're just constantly moving. Slowly but surely, grandma will get there. All right, so we're constantly moving upward. This is a positive slope on your line. So we're looking at a constant velocity. This is a constant increase in velocity. So know those differences between the different graphs, and we can, and I think that'll strengthen you in what your in your ability to read a graph on your quizzes and tests. Aha! Here we go. That's a triangle X over through a triangle A. What I mean is displacement. Now, finding a displacement earlier on a distance versus time graph or a velocity graph is very easy. You just simply are adding up the displacements and you're looking at the changes of position, and you can find your displacement quite easily. But this is not a velocity graph. This is a what? I have velocity and I have a division of time versus time, or velocity over time. This is an acceleration graph. You bet it, buddy. You bet it. This is an acceleration graph. Now, a couple of you had some questions earlier. Like, Mr. A, how is this a vector if you just told me that you went from 35 miles an hour to 0 miles an hour in 45 seconds? How can that be a vector? You didn't give me direction. Okay, that's fine. It still is a vector. It still has direction. But we don't find its displacement the normal way of simply just adding up paces and comparing it, drawing triangles. We do it very differently on this graph. The way you find displacement through an acceleration graph is by getting the area of the marks of the graph itself, of the progression. I'll repeat that again. We're trying to find displacement using an acceleration graph, so it's quite differently. It's just expressed differently. We can find it with the information that's here on the graph. The way we do that is by finding the area with the graph. Yes, for those of you that know rhombuses and know that trapezoids, the area for that, that's great. And if you show me the work on your quizzes and tests, that's fine with me. That's great. But for this particular lecture, and the main thing that I just kind of want to simplify for everyone is by showing me the work through right triangles and squares. And yes, a rectangle is, by definition, a square. A square is just 4 sides that make 4 right triangles. So I'm going to use it interchangeably, but it's okay to say rectangle and square. I forgive those kindergarten teachers around the world. It's cool. Length times width is the area of a square. 1/2 base times height is the area of a right triangle. And just for kicks, I'll just show you really quickly why that is. Because this is a right triangle. And if this is 6 and this is 7, if I multiply base times height, then I'm finding the area, or the length times width, I'm finding the area of a full rectangle. By cutting it in half, I'm finding the area of just this triangle. So that is why 1/2 base times height even works in the first place. So we just need to find the area of the graph itself. Part 1. The first thing you need to identify is what are the shapes that you're going to solve for. So as you can see over here, we are solving for 3 individual shapes. We have 2 right triangles, triangle 1 and triangle 3, and the square in the middle, triangle or square number 2. We simply have to do the next step, which is find the area of those shapes. Now, for those of you that are uncomfortable measuring this, it's okay. We can use a direct measurement. Why? Because here we have time in seconds, and here we have our velocity in meters per second. So those two those two measurements kind of are the same, so we can simply just measure to find our our area. We can use a direct measurement. So let's take a look at triangle number 1. Boom! Triangle number 1. 5 times 5 because within 5 seconds, and 5 is our meters per second at this point right here. We have the base, we have the height. We divide it by 2 and we get 12.5. Some of you already did this in your head, but this is square number 2. 5 times 5 equals 25. And yes, here we have triangle number 3, 1/2 base times height. Over here you can't see it on the camera, but this is 2.5 seconds because it goes from 10 seconds here to 12.5 there, and that is 2.5 seconds times 5. Bam! We have the area of all the shapes within the graph. You add them together and you get your displacement of 43.75. And that's pretty much how you find displacement. Now, can displacement still be 0? Obviously, yes, it can. And I'll show you an example of where we can find that. Here we have a velocity versus time graph, and this is probably very different from a lot of the graphs that you've seen. If you've seen this type of graph already, you are ahead of the curve in this particular class. But what do you notice? Most graphs, they go like this, boom, boom. You have your X and Y, but you're only dealing with one quadrant. In this particular graph, what do you notice that's different? In this particular graph, you see that you have 2 quadrants. You have a negative quadrant for your y-axis, because certain things can have a negative velocity. How do we find out the displacement of this? Obviously here, this is decelerating, and it's decelerating all the way down into a negative territory. So, first we find our shapes. So with this particular line, and I'm going to do this in red so that way you can kind of see the line. This is my line right here, right there. What I've done though is I created my 2 right triangles, and I find the area of those 2 right triangles, and then I'll find my displacement. Triangle 1, 5 seconds. And we have a positive 8 meters per second. So we simply do 1/2 base times height, which is 1/2 5 times 8. And then we get 20 meters, okay? Right. Now the next thing that we do, you notice something different over here about this particular triangle. We have a negative 8 for this particular triangle. And with that, we end up getting a negative 20 for our area of that triangle. We add them together, 20 plus negative 20 equals 0. So our displacement that we see in this particular acceleration graph is 0. Please study hard, please look at the notes, and please pay attention in class so that way you can have the most successful time as a physics student. Late.